Shall we start the session?
I think we can start the session.
Okay. Thank you, Shumit sir. Right now, we are going to start session 12 of this ongoing FDP. And I, on behalf of the organizing committee, welcome you all to this session. It's Saturday afternoon, and we are learning so many new things about this quantum computing. In this session, we are going to learn about autonomous edge computing from Mr. Atanu Roychowdhury. Before we start this session, let me take this privilege to introduce him in front of you. Mr. Atanu Roychowdhury is the founder and managing director.
Rosita ma'am,
Yes,
ma'am,
yes.
can you please request sir to switch on his camera for a minute for the introduction?
Okay. Atanu sir, is it possible for you to switch on the camera so that we can have?
Absolutely, absolutely.
Okay.
If you see me phased,
Yes.
I just wrapped up a industry visit from a bunch of students, right? So from students to faculty. There we go.
Okay.
Thank you, sir.
Thank you. Thank you, sir. So as I left, Mr. Atanu Roychowdhury is the founder and managing director of Dept. He is a techno-functional consultant for IoT, AI-led curriculum development, and digital transformation ventures. He is a technology advisor to the Ranmir Foundation and its incubator. He is a part of the board of members at the ATAL Incubation Center, Sikkim Manipal University Technology Business Incubator, KL University Technology Incubators Foundation, and ATAL Community Innovation Center at SGT University. He has developed curriculum and taught innovation and entrepreneurship development, Internet of Things at Calcutta University, and intelligent process automation at GIS University. He has provided delivery and solution support to Altec Global Sales team for over 100 IoT solutions. Prior to Altec, Atanu was a member of technical staff at Infosys State Labs, Harvard Sensor Networking Lab, Telcord Deer Advanced Technology Solutions Lab, and Blue Highway. So he has postgraduate degree in computer science from IIT Guwahati and Harvard University. He is a senior member of IEEE and CSI. He has published over 35 papers and patents in the area of IoT and wireless sensor networks. During his active research career, he brings in over 2 decades of transitional professional experience. So with this brief introduction, may I now request Mr. Roychowdhury to continue his session. I think this introduction was quite brief, which I told you about his career. He will tell us more. Sir, the platform is yours.
Absolutely. Thank you. Thank you so much, madam. Right. And I see that there is quite a lot of participants. I see that there are almost 70 participants, and a very, very good afternoon to all of you. I know it's post-lunch, almost getting towards tea time, right? So rather than been uptight about the session. Let's keep this a little open-ended. Let's keep this session a little bit about our experiences, right? As Madam Rachita aptly mentioned, I am essentially somebody who comes in with a background of building systems, right? Now, over time, that has translated into deployments all over the globe, right? And I'm not much of a quantum computing person, let me put it that. For me, a quantum computer is essentially very similar to Feynman path integral, right? You have, if you can frame a question such that you have variations which would cancel each other out, then they will cancel each other out, and you get to the shortest path, right? For me, that's my abstraction of a quantum computer. But over time, we are also computer engineers, right? And that means any kind of problem that we come across, we tend to create an abstraction on top of it, right? And work with those abstractions. Just for my curiosity, I see there's a lot of people here, right? If I could just go around the room and probably do a quick check in terms of what are the subjects that you teach in your respective institutions, that would be very, very helpful. If you're not able to speak currently, you can also type it. That's fine. Yeah, we got cybersecurity and networks. We got physics. Just trying to understand the audience, right? Computer networks, excellent. What else we got? Theory of computation. I'm also trying to keep track of how many people are still in the session and how many of you have slept off. Right. Let me rephrase my question a little bit, right? How many of you actively code? Shubhendu said that he's actively coding. So we have 1 in 70 participants, faculty members who are actively coding. And that's interesting because we are systems builders. We want to build systems, whether it is a distributed system, whether it is a networking system, whether it is an operating system, whether it is a file system. I did not get I did not get responses from faculty members who said that they were teaching operating systems and so on and so forth. Right now, building a system means that, or rather, if you have not built a system, right, then the complexities of building a system are not very, very apparent. In my experience of building systems, especially computational systems, we tend to mimic what we see around us. We tend to mimic the societal protocols, essentially, right? In order to, how do we think certain situations should be resolved, right? For example, if I wanted to do some deadlock management. We look at the first example we teach is how does a deadlock form, right? If we wanted to talk about semaphores, right? The word semaphore itself comes from signaling systems in railways. If we want to talk about consensus building, we look at election protocols and so on and so forth, right? So that essentially brings me to today's topic of autonomous edge computing, right? Now, there are two parts to that, right? One is the edge computing part. The second is the autonomous part. What are the trade-offs, right? That's important. What are the trade-offs that we will need to encounter if we are building a system, right? So the fundamental aspect of such a system is essentially, if I were to distribute my computing, if instead of computing everything in a single computer, if my intelligence or my computation was distributed, then how do I build a better system? That's the crux of the question that I'm trying to answer. And in any of these systems that I build, what are my levers? What are my trade-offs or choices that I can bring into the picture, into the equation, right? And there are multiple axes of deciding on what a system should be. That depends on the particular application that I'm building, right? So there are aspects of, let's say, for example, computation versus communication, or say the carbon footprint versus the performance, the security versus the usability, right? The latency versus the consistency, right? The traceability versus the privacy. So there are a lot of these questions that come about. And in any application that you build, whether you are building a quantum system or you're building an IoT system or you're building a cellular system, right? Or you're building a smart agricultural system, whatever you will, the kind of trade-offs that you get into, right? That's where the research questions also lie. That's where the optimization of the solution itself lies, right? So having said that, let's start off with trying to understand what autonomy itself is, right? As faculty members, most of us have a code thinking, right? What we see in the textbooks is all very nice and clean, and there are specific protocols that we use for in our code, right? But when we start thinking about deployment, it is messy. I remember there was one example where we were building a seismic monitoring system out on Mount Ravantadu, and we had a bunch of sensors. We carried those sensors on our backpacks up the mountain, and we had an excellent system that was going on, which could detect seismic activity. And one of our sensors was giving us very, very good data. So we downloaded the entire data, right? In fact, to the point that our batteries were depleted. These were large car-sized batteries, or not car-sized batteries, car battery-sized, right? These were large batteries. And we got a signal from one of the nodes, and we were happily downloading all that data, right? Except that after we started analyzing the data, we found that our sensor had a DC bias. So all the results had a DC offset, and therefore they were above the threshold. Our system started to think that, hey, this is all very, very important data, and we downloaded everything, right? Which basically means that the entire data set was garbage. And we learned to program that system better so that we don't have to haul that battery up the mountain again, right? So when we get into this kind of code thinking, right, we think about function logic, we think about loops and algorithms and all of that, right? But we seldom think about, where does this code run? Is it running on a server? Is it running on a bladeless, or rather on an edge computing device, on a Raspberry Pi, which has no heatsink? Can it run for 24/7, right? Is it running on a smartwatch? Is it running on, let's say, a smart bulb that is out on the street? Where is this code running? What is the environment under which this code is running? Is it outside? Is it going to be raining there, right? So that's your deployment thinking. Your deployment thinking starts when you start, not only thinking about the code itself, but you start thinking about where the code is deployed, the location, the physical location, the network, all the intermediate hardware constraints, right? When somebody, I believe that all of you will, are joining in today's session from your homes, and all of you have a very, very nice internet connection at home, right? Have you seen the mess? If you are having an overhead, an overhead cable come into your house, right? The junction boxes are a mess. Did the person who wrote the switching logic for that particular junction box ever think that it was going to be deployed on the top of a lamppost or a broken pole somewhere, where it is going to be the box in which it is housed is going to be open half the time, it is going to be exposed to the elements, right? But that's what deployments are. Deployments are messy, right? You don't get to know what is going on. There are junction failures that happen because the junction was exposed to the weather and it rusted, right? There are trade-offs that come along with, with the location, right? Is your network availability, is your wireless network availability there, right? What is going to be your mechanism for, let's say, graceful degradation, right? If a system fails, then what happens? And that is significantly a part of what deployment thinking is about, right? So the first thing that I want to probably highlight in today's discussion is that code thinking is not necessarily the same as deployment thinking. Deployment thinking, you have to go out there and put the system out, and it's going to fail in ways that you have not thought about, right? The second thing I want to bring in over here is, as faculty members, we don't want to write code. We don't want to write elaborate code. Let me be very, very frank about that. Because we don't write code, we do not know what are the software engineering challenges that are associated with that code. I can guarantee that none of you have used a system where you have a development environment, a testing environment, a staging environment, and a production environment. It is not feasible, right, to build out code in that, to manage code in that format. When you write 100 lines of code, you can write it on your computer and you can run it, right? But when you are writing 5,000 lines of code, when you are writing 10,000 lines of code, the bigger challenge may be scrolling through the code than the code itself, right? Now, most of us are used to writing this kind of small code bases. Typically, these are what we call our scripts, right? A script is functional. It works in your environment, right? You have all the dependencies for the code to run on in your laptop, right? That's great. But this is a code that you cannot really give to a customer. That's not code it's not hardened yet, right? So typically, whenever we talk about giving the code to a customer, right, that code has to have some kind of a UI to it, right? Now, whether you build that UI in Tkinter, whether you build that UI in React, right, or HTML code, that's completely up to you. But the idea here is that when you build a utility, you have to take the customer's perspective, right? And utilities usually take, building out an utility an executable that can run on somebody else's computer means that you have to put in some thought about the packaging of that system, right? Scaling up, you look at server-grade systems, where part of the code runs on various kinds of server systems. And if there is a front end to that, then you have to figure out a way to get to the front end to your device where it is going to get used, right? Most of us are used to the web interface, right? So that is definitely one interface of building out a system. We are very familiar with REST-based protocols. We are very familiar with SOAP-based protocols, right? But when you are putting out a deployment, right, say, for example, in a factory floor, right, where decision needs to happen based on, a camera that figured out if a particular product's, is not good, right, then the decision has to be made then and there, right? The decision does not necessarily come back to the server systems, right? It's a decision that is made at the edge itself, which means that the resolution also has to happen at the edge, which means that you are talking about human-computer interfaces, right, which are residing, on the near the machines themselves. Right? It's not a server that is serving out that interface. With the advancements of AI, there are multiple such interfaces that are coming up. The web being one of them, voice being another one, gesture being another one, right? So there are multiple interfaces that are coming up, right? We need to deal, when we are looking at these deployments, right, the user experience of such a deployment, the intelligence of that deployment really boils down to, when we talk of something as being intelligent, what we understand is how usable is that system. It might be the most intelligent computational model, but if it is non-intuitive to the user, they will not rate it as a usable system or an intelligent system. Right. So somehow, when we are discussing the concept of autonomy, when we are discussing the concept of intelligence, there is a user aspect to the entire thing. Right. And that's not the end, right? That's just a server grade system. Right? Beyond that are enterprise grade systems. And that's in software only. Right? When we have an enterprise grade system, say, for example, I write a script where I can sort 1 billion numbers or say 10 billion numbers very, very effectively, right? But when I'm building an enterprise system, I need that system to be accessible to all my employees, right? If I need that system to be accessible to all my employees, then my employees need to log into my system with their corporate email IDs. Which means now I need a mechanism so that their Active Directory with their Microsoft-based system, their LDAP systems, or their OAuth systems, they need to be integrated in, right? So eventually with these enterprise-grade systems, what ends up happening is I end up spending way more time on these integrations than on the core heart of the problem itself. Right? So deployment is also about, as I said, deployment is about usability. So, and usability means usability to whom? I can think of even larger systems, right? Say, for example, if I think of systems which are citizen grade, for example, an Aadhaar or a tax portal that's going to be used by 1.5 billion people, or maybe not that many in India. Maybe we're talking about 500 million people, right? That's a massive system to build. Even larger systems are planetary grade systems. The Ubers of the world, the Googles of the world, right? These are planetary grade systems, right? The way we think about these problems of these systems is fundamentally different to the way we think about writing a script, right? Because if I were to build a Facebook, right, I would maybe throw 1,000 or 10,000 servers just for their login process. Right? So as we look at the complexity of these solutions, right, and it gets complex by orders of magnitude. So one question to us is, how do we collaborate? How do we create collaborations within the university ecosystem, within the colleges, in order to even try out to build these systems? Remember, today we see all of this because some universities in the US decided to come together and create a distributed environment like Planet Lab. If we had not made Planet Lab and made it an accessible system to the universities, we would not have cloud computing today. So this collaboration is mandatory, right? Going beyond where the curriculum is mandatory, right? That's the first thing I wanted to talk about. A change in our thought processes about deployment. Where do we deploy? Unless we know the deployment environment, the users of this system, we will not think about the usability or the effectiveness of the system. Right? In today's systems, what we are seeing is, I mean, for those of you who are, I don't know the audience here, but for those of you who are old enough to have seen the IT boom in the late 90s, early 2000s, right? A typical organization would, today you use Gmail, today you use OneDrive, Google Drive, all of these things, and you kind of assume that there is redundancy of your data. You take a photo on your phone, and it is synced to your Google Photos. But in the late at the turn of the century, what was happening was every organization, they used to maintain their own server groups, right? They used to maintain their own server rooms, and they used to run their own email servers. They used to run their own file servers. They used to run their own networks, right? So typically an organization of maybe 200 people would have a server room, and there were IT people there who would manage that setup, right? Would, 3-4 people who would manage that setup, right? With the evolution of the cloud, what has happened is, if 100 companies had 4 people each running a IT server room, now all those services have moved to the cloud, right? If those services have moved to the cloud, instead of those 400 people, network engineers, now I have maybe 100 people or maybe 40 people who are managing the data center. It is relatively easy to deploy a service in a data center, right? It gives me the advantage of there being disaster recovery. Should I need it, I have multiple availability zones that are there. It gives me peace of mind because my data is not lost. There is business continuity, right? It allows me to create collaborations. I can open up a Google Doc and share it with 3 or 4 people, right, and work on it together. And I have multiple service models that are available. I could ship my server to a cloud provider and say, just pay. I'm just going to pay for electricity and maintenance, right? I am using the rack as a service, right? I could do that, or I could just play on the infrastructure and buying a bunch of VMs, right? Or I could start looking at the platform itself, as a service, or the software as a service. Now, each of these deployment topologies, if you will, right, they come with their own set of pros and cons. Today, I can go in and for IoT-based solutions, I can ask for an IoT cloud provider, right, or an IoT cloud as a platform, right? But in doing so, what is happening? Somebody has to deploy my functionalities onto that cloud. That's not going to auto deploy. And the moment I deploy that, right, there are questions about what is the privacy of the data that is going in, right? How long does it take for me to compute something? Should I be setting up a virtual machine and running and letting my code run on that? Right, that's a possible mechanism to. That's definitely a possible mechanism to have a system out there. Or am I going to use something called a Lambda function? right? As and when that particular functionality is required, a server is spun up, right? If I decide to use a Lambda function, then how do I ensure that my code is getting injected into the Lambda function properly, right? And that brings me to setting up a code pipeline, right? Setting up a complete CI/CD pipeline, a continuous integration, continuous deployment kind of a pipeline, so that I write some code on my laptop, right? I commit the code, right? The code pushing that code into a JIT server triggers the Lambda process, the CI/CD pipeline. That code gets pulled in somewhere, it gets built by a Lambda service, it gets deployed on a particular VM, right? So there are multiple ways I could think about of this deployment, but at the end of it, I understand that deployment is centralized. So I moved from having independent IT server rooms in each organization to a more centralized architecture where decision making was at the cloud. And having done that, now I'm thinking about, hey, how do I move the computation back again to the edge? Now that is a little bit of a, doesn't it strike as as maybe a reversal of our architectural choices? We centralized, and once we centralized, we decided to start moving things out to the edge again. How do we resolve that dichotomy? For those of you who are coming in from a database system, right? Now, until a few years ago, SQL was king, and every other system that we built with relational databases, right? So one form or the other. Those of you who are old enough, right? If you read into any of the papers by Michael Stonebreaker, right? The general consensus was, or rather Stonebreaker's perspective always was, hey, you give me a problem and I'll give you a database that is at least an order of magnitude faster than a relational database. So he never got along with God. And in pursuance of that thought process, we created systems like Vertica, we created systems like HBase, we created systems like Cassandra, right? These are all column stores, right? So we created a completely new, different set of databases. Today, the flavor of the of systems are essentially something which is a NoSQL database, right? Something like a Mongo, right? Now, Mongo gives you that flexibility. It says that instead of being a database, of being a relational database, I'm going to be a store of documents, right? And things are good because I don't need to formally bind down the data model, right? I can still create a database which has data as documents, right? As JSON files, if you will, or or images or things like that, instead of having it in a relational database. But the challenge is that for every query that I ask, I need to start parsing through all the documents to figure out an answer to my problem. And that is slow. So the cost of flexibility is the performance of the system. And now what we do is, once we have said that, yeah, sure, this is the kind of data that is going to be coming into the system, this is the kind of documents, and we have a fair sense of the type of documents in a steady state system, we said, okay, now that we know what the document structure is going to look like, let's go ahead and build a SQL again. Because I want the performance. So you have seen that happen with database systems, where we went into the flexible model, and then again we came back to a more rigid model, right? The same thing is happening with cloud, right? We said, okay, let's put all our servers and everything onto the cloud. Things are happy, right? But then again, we figured out, okay, perhaps it's not a good idea in a number of use cases where all the data is going to the cloud. Right. For example, if I launch a new smart camera system, and I decide to improve the security of the city and put a bunch of cameras all over the city for traffic surveillance, it would not be a good idea to send all the data frames, all the video streams back to the cloud server. If I'm trying to count how many people or how many vehicles are crossing a particular street, or what is the throughput of a particular lane or a street, I need a number. So if I can compute that number directly on my smart camera, I just need that number. I don't need to push back my entire data frame to the cloud, because it's going to congest my network, right? And it's going to bring in a lot of cost to transcoding all the video streams. And that is cost. So I'm stuck with the choice of saying that, hey, do I make my edge system a little bit more smarter? Do I put do I improve its processing capability so that my edge system is going to cost me, let's say, $20 instead of $10, right? Or do I send the entire data back to the cloud and pay the money there, plus the cost of moving the data from the camera to the cloud itself? And video data, as you know, is very, very bandwidth consuming, right? So herein we see this pull away from centralized systems, if you will, right? And that kind of takes me to my next slide, right? I'm coming at it from an IoT system because I have been building and deploying these massive global scale IoT systems, right? Systems with more than 1 million devices, 10 million devices in the network, right? And at that scale, right, not every device can afford to wait for the cloud. So there are two main aspects to that. First is that not all data needs to travel far to be useful. And the second thing is the cost of sending that data, right? So the entire idea of having edge computing is to move the compute closer to the data generation. And why? Because we expect it to reduce latency, we expect it to save bandwidth, we expect it to increase the resilience of the system, right? We expect it to be useful in real-time low connectivity or privacy sensitive settings. That's the idea behind it, right? So if we didn't see the emergence of IoT devices, probably we would not have thought so much about moving away from the cloud infrastructure. But yeah, of course, once we have that capability, we cannot unlearn that, right? So let's see what else can we do out of this network that we are building, right? Any questions so far?
No question in the chat box. Participants, if you want, you can ask him question directly.
We have new generation cloud using quantum computing. I think, where did that question come from? Do we have a new generation cloud OS using quantum computing? I think you should really go and see what a quantum computer look like. I think that perspective is missing. In terms of what does it take, right, to build a quantum computer? How is it housed? How is it cooled? Right, depending on the technology that you use, right? Whether it's a private enterprise like DBase or or even IBM, right? The qubits they need to be at near 0 degrees Kelvin, right? For a cloud computing environment to work, a typical cloud computing environment, given the volume of okay, let me see if I can describe this. If you walk into a data center, right, typically what you will see is a rack of towers, or let me see if I can go back to this, right? So this is typically what a data center looks like, right? In this, what you see as the black boxes, they are called racks, right? Now, each of these units are typically measured in, you'll have a 22U unit or a 24U unit, right? So there are slots in each of them. These are called units, right? And each blade, in between each of them, they are called blade servers, right? So these blade servers, they typically have a height. They either consume 2 units or 1 unit blade servers. Within each 1 unit blade server, there are going to be a bunch of servers that are going to be set up like PCI cards, right? So there's going to be about, say, 8 or 10 servers, right, that are going to be housed in each blade server. Each of these servers are going to be multi-core, right? Each of them are going to be 32 core to 64 core, right? That's what you have in one server. If you are running a data center, the idea here is to combine the collective computational needs of multiple organizations. And typically, the major cost in a data center are its energy costs. Right? So it has to be cooled, it has to be, but even though it has to be cooled, it has to be cooled typically in the 10 degrees centigrade, 10 15 degrees, 20 degrees centigrade kind of temperature range, right? Now for those of you who are using gaming laptops, right, we find that your gaming laptops are coming in with a 150-watt charger, right? Your mobile phone comes in with a 5-watt charger. So when you are putting in so much computation together, right, there is already a lot of heat that is generated by the computational system. So companies which are operating these data centers do tend to minimize cost by shifting to cooler climates, so that it's easier to dissipate out that all that heat. But quantum computing is a different beast altogether. You are not looking at 280 degrees, 290 degrees Kelvin. You are looking at near absolute zero Kelvin, right? So to build a quantum computing system, an OS cloud using quantum computing, we are probably not there yet, right? The IBM's entire infrastructure allows you access to the reason that it is limited to only 10 minutes of access is because it's only a very, very few systems that are available throughout the globe which are doing quantum computing. They are housed in specific environments, right? So it will take some time before they are available as commoditized cloud systems. That's my answer to that. Any other question? Good question, though. And I think if there are no further questions, I'll move on. And there are, why are we talking about this autonomous edge computing, right? I've put up 4 examples, right? I've put up 4 examples of, say, a smart drone farm, an autonomous vehicle, smart living spaces, smart factories, right? And these are all places where you need that autonomy, right? These are all places where you need that autonomy, but the fundamental architecture of these 4 systems are very, very different, right? For example, when I talk about smart living spaces, right, which are essentially smart homes, the main driving force of that application is comfort and convenience, right? So the latency requirement of an autonomous decision, right? If I switch off a bulb, I want it to be switched immediately, but if it switched off in a couple of seconds, would it really hurt me? It wouldn't, right? Yes, if the system fails, then I, as a consumer, may be impacted, but is it really life and death? Perhaps not, right? So the fundamental requirement in this domain, if you will, is very, very different. So building autonomy into a smart home application is very, very different from, say, the examples of a smart factory, right? Where I need testing, quality control to be done, say, on the factory floor itself, on the assembly line itself. Right. So there could be products that are being manufactured at some place. You're going down the assembly line. You have a camera that is scanning for material defects, right? And you need to take an action whether to keep that item in your packaging line or to discard it from your packaging line, right? So you have to be able to make a decision and activate an actuator to push that out of the assembly line so that it is either returned as a defective piece or is reworked upon, right? Or is repurposed for whatever reason, right? So with some of these smart factory automation systems, we see latency requirements of the order of milliseconds. And that's important to ensuring that the quality of the product remains consistent, right? Autonomous vehicle, another area, right? When we are talking about vehicle to vehicle integration or vehicle to infrastructure integration, the decisions need to be split second, right? But at the same time, what split second is a split second, right? We still have the physics to deal with. We still have the momentum of the vehicle to deal with, right? So if I cannot just go in and slam down the brakes for whatever reasons, right? But it has to be something that can contain the momentum of the vehicle itself, right? So building out autonomous vehicles, looking out for traffic, yes, it has to be done fast, right? But it has to be done fast in the context of the ambience, right? At human-ish speeds, or maybe slightly faster than speed. So we can clearly see that there is a difference in terms of the fundamental underlying requirement of the solution itself, right? If I am building an ATM, right, I want the user to set a pin, right? I want to verify that they have entered the right pin and before I give them access to their money. If I'm building a smart vehicle and I apply on the brakes, I don't want the brake to show me enter your pin before the brake is applied. So there are situations where we are willing to trade off even the acid properties. There are situations where privacy becomes very, very important in financial systems and things like that. There are systems where the operational side is more important. The response time become way more important than the privacy aspects of the solution, right? So we see a plethora of examples where the decisions must happen instantly. Instantly, I'm putting that in quotes because there has to be a quantification of instantly. Is it sub-millisecond? Is it a few milliseconds? Is it seconds? Is it of the order of minutes, right? What really do I mean by instantly, right? The systems need to become autonomous because my internet connectivity, right, my control flow to that particular equipment might be unreliable or non-existent, right? Third thing is that the data privacy, right? Sometimes data privacy demands local control because that data cannot leave the geographical area, right? And while the cloud is an option, the cloud bandwidth at scale is very becomes exponentially expensive. So the entire concept of autonomous edge computing is to let the devices adapt, collaborate, and kind of recover on their own. And that's really the key architectural thought process behind it. Do you build a centralized system where a single cloud server makes all the decisions, right? It's fragile, right? It fails completely if the central service is down. Versus, do you have a more decentralized, right? In whatever shape or form of decentralization, right? Whether you create a mesh, whether you create a hierarchy of decentralization, not going to get into that, right? But you are essentially saying that I will have autonomy at the edge itself, where devices are, they kind of follow their shared rules locally. I don't know if any of you are aware of, you know, of cellular automata, right? Or, seeing the emergence of systems as smaller pieces kind of come together, and there are very local rules that kind of apply. So you'll see biologically inspired systems like cellular automata, or for example, ant colony optimization, things like that, right? But the idea here is that devices follow a shared rules locally, right, without central approval, which makes it more resilient to network failures, and it can survive partial outages. But at the same time, there is now a problem of synchronization between local states and global states. So if you're trying to build this kind of autonomous systems, we must have some kind of a control loop where we kind of monitor, we analyze, we plan, we execute, and we learn, right? So that's the core idea. You sense, think, act, learn, right? That's how autonomy works, right? So it's not that I should be allowing only edge-based decisions, but why I allowed that decision, that learning should be propagated to the cloud so that that learning can be federated, that learning can be accumulated from multiple edge devices. New truths about the entire network can be discovered, and they can be propagated back to the edge itself. Right? That's the core idea behind it, right? You sense, think, act, and then learn. Right? That's how the edge system evolves over time. So autonomy essentially means that there is a continuous local feedback, plus there is statefulness, there is memory that is involved at the edge, right? If the device is acting completely independently, it's an autonomous system, but it's not an edge component. It doesn't have any connection with the mothership, if you will, right? What are these trade-offs? How are we doing on time? Okay, I'm going to take a very short break. Just give me 1 sec. I'll be right back. Yeah, my apologies. Yeah. So what I'm putting in front of you, with the assumption that many of you are coming in from a computer science background, this is something that you teach your students, right? I want you to go back to the roots of computer science itself, to the foundational philosophical questions of building out computational systems, right? As of today, we still build systems that are very much aligned with the von Neumann architecture, right? But it's not very unlikely to imagine that tomorrow's systems are going to be fundamentally different. Yes, there may not be quantum computers, in the next few years, right? But is it not possible to envision a system which is probably a GPU that runs a LLM, and the upgrades are LLM level upgrades, and you have custom GPTs on top of that for do your particular functions? It's very much possible to imagine, instead of a Chromebook, you tomorrow have a ChatGPT book. That would fundamentally alter how you interact with that system itself, right? How you interact with, would you need a programming language to converse or write a program on top of such a device? Probably not. You probably need to write a very good prompt, right? So these are fundamental questions of the computational model itself that we follow, and what does autonomy really mean, right? What are the trade-offs, right? And some of these trade-offs you are probably familiar with, right? So I don't have to repeat them as much. And because they're trade-offs, there is a Pareto optimality that you will get out of it, right? It is not important to have an absolute, it is either computation or communication. No, it is a trade-off. What is good enough computation, right? So this kind of when you are getting into systems building, right, in especially these distributed systems, right, it's a lot about Pareto efficiency. What 20% can I change to essentially ensure that 80% of my system is operational, right? So we try to look at where we are able to make informed compromise, right? Instead of trying to optimize one thing or the other, right? But then the important question is, which trade-off axis will dominate your context? I just previously explained that, 4 different contexts, right? Of smart drones or your autonomous vehicles, right? But in your particular application of interest, what is that trade-off axis that is dominating, right? It could be compute versus communicate. That's the first thing that we learn in computer science, right? If you do less computation, you have to send the data over to somebody who has better computation. So either you compute locally on a more expensive device, or you move that computation to somewhere else. You send the data over to somewhere else where it is cheaper to compute. Right? What's the tension here? The tension is that the more you compute locally, the less you need to transmit. But you trade that central insight for local autonomy. That's the trade-off. Right? So the autonomous vehicles are computation heavy, whereas security systems that I talked about earlier are communications heavy. Right? So where do you put your computation? And that will depend on device to on solution to solution. In many solutions, you may not have such a clear hierarchy of centralized and decentralized. There may be 10 different devices, right, in between your edge computing and your cloud computing. You may have a rain computing layer, you may have a fog computing layer, you may even have a dew computing layer, right? But how much is to be computed where? That's the key question. You could have a question about your carbon footprint and your performance and your AI performance, right? where are you going to draw your inference? Are you going to use a cloud GPU for ultra low latency, right? Or are you going to use something that is slower but greener, right? Now, most of you, when you use your mobile phones, most of your phones today have very, very good, you can browse the internet. You can do anything that you want on the internet with your mobile phone, right? Now, if you can do anything that you want to do on the internet with your mobile phone, and that mobile phone charges with 5 watts of power, why does your laptop consume anywhere between 65 watts to 150 watts? Because that is power that is getting consumed, which means that is power that has to be generated by burning coal somewhere. When you have an LLM system and you ask it to type out an email for you, it is consuming energy. So is it a good system? Depends on your application again, right? That's again a trade-off. Are you going to have higher performance at a carbon and you're willing to spend that carbon footprint? Or is it okay to have a slower system? Right? And it's not just the cost of the carbon footprint of computation. It is also the carbon footprint of the entire transmission, right? It is the carbon footprint of the storage itself. Because all those SSDs that are running and storing your device are not working without electricity. So there's a lot of energy that is getting involved, right? So is your solution, when you are designing a solution, is energy going to be your focus? Is the performance going to be your focus, right? So that's one axis of your system, right? I think I kind of talked about this a little bit earlier, right? In terms of your security versus usability. Are you looking for a Swiss Army knife? Are you looking for your ATM level security, right? So are you going to have, does it make sense to have multi-factor authentication on field sensors? Well, it depends on the sensor. If it's a sensor for remotely unlocking my door, right, at my home, I want multi-factor authentication. Right. So even in cases where, edge devices, depending on their application, the requirements for security might be there. Right. The tension is that every lock, right, every lock kind of adds friction. Every abstraction, security abstraction that you build, whether it is to enter a password, whether it is to have a secondary, SSO authentication, or RSA key authentication, or authentication like multi-factor authentication, things like that. Every one of those locks, they add friction to the usability of the system. So when you think about a maximum security system, right, it can make the system bloody unusable, right? While when you look at maximum usability, it increases the threat surface of your attack. Right. So where's the needle over there? What are the security requirements in my system? Right. That's why it's important to, when in systems design, it's important to kind of understand those trade-offs. Right. Traceability versus privacy. That's another axis. Right. Do I build a blockchain-based system where I can trace everything up? It's a public blockchain. Everything is on immutable records, right? I want traceability. I want the ability to audit, verify, and reconstruct events. I want to be able to reconstruct data lineage, right? All of that. Or should I focus on privacy? I should protect the individuals or organization sensitive data. In the age of AI, right? In the age of large language models, right? my policies have gone for a toss. Earlier, if I was an organization and I could say that, the HR has access to this information, the CEO has access to this information, the employees have access to this information, right? Now, if an HR accidentally just shares her Google Drive or OneDrive with Copilot, that entire data set has been learned from. So how do I enforce my policies any longer? Here again, there is a tension, because the better you can track events, the more personal or operational data you risk exposing. Right? Do I track data from farm to table? Do I bring in that kind of traceability through the network? Or do I anonymize the data? Do I place more emphasis on PIIs, personally identifiable information? Right? That's another area of tension. Another one, your consistency versus your latency. Consistency inherently means that there has to be synchronization. You have to solve a distributed synchronization problem, because you will not be consistent until you are speaking from the same ground truth. And if you are trying to be consistent, you have to give it the time. Or is latency more important to you? Do you need a fast response even if it is wrong? For those of you building AI systems, it's a lot like your LTSM systems. Right? Humans, right? We have a few things when we are going through this whole talk, right? There are a few things we have in our mind, and we'll be able to respond very, very quickly from those things. But if I have to go and think about something and reflect upon something, it is going to take time. Right? So the tension again is what? The tension is, if I chase instant responses, it often means tolerating temporary inconsistencies. If I want to chase global consistency, it means that I've got to wait. Because that messaging, that messaging has to come back. It goes back again to the foundations of computer science, Byzantine generals problems, message passing and consensus building. I had alluded to this earlier. I had said that, hey, your mobile phones take 5-watt chargers. Your laptops are taking, they need a 145-watt charger. Why? The primary reason being that, Intel being Intel pursued a CISC architecture. Whereas your phones are all Snapdragons, they are running on a RISC architecture. So whenever it is RISC architecture, you have a simpler process, you have a simpler hardware, right? So RISC favors energy efficiency and predictability. CISC favors dense computation. So whether you want to run tiny ML on an ARM Cortex-M versus AI acceleration on a x86 server processor, right? That again will come down to your application. I'm just putting out the layers. I'm just putting out different layers over here so that you have a sense of what is going on in each of them, right? Are you going to have a deterministic system, or are you going to have a probabilistic system? Right? Everybody knows typewriter. You press a key, you will get exactly that same hammer. You are using a lever, the hammer goes up, you get the same number, right? But you use an Enigma, there are 3 levels of permutations that are happening, right, before your number goes and gets, produces an output. And it led to the development of some of the first, or probably the first, computational model to be able to crack the Enigma. So determinism gives predictability, right? But it cannot adapt to uncertainty. If you have probabilistic methods, they adapt, but then they are harder to certify, which is the problem that you are seeing with explainable AI, right? Your entire logic sits as weights within a neural network. To give you an example, do you have, like, if you have a drone network, does it go on a fixed rule drone navigation? Is it a line following algorithm, right? Or is it an ML-based adaptive pathfinding solution? Because deterministic is very easy to understand for people coming in from a programming background. Programs are deterministic. That's why we are able to debug them. Thoughts are probabilistic. That is why it's very hard to read a person, but it is easier to read a program. Right? If you are building out multi-hop networks, right? What do you favor, range or hops? And we cannot forego our Maxwell's equations here, right? The power needed to transmit is going to be it's going to be inversely proportional to the square of the radius. So larger range means a lot more power that you need to transmit with. Or do you break it up into smaller parts? Do you want to break it up into smaller parts and have intermediate repeaters? That leads us to different architectures, deployment architectures, right? Especially in areas of low connectivity, especially with a lot of these agricultural IoT solutions and things like that, right? What do you facilitate? A multi-hop, mobile ad hoc kind of a network, or a high power, long range kind of a network, or a microwave network, right? What hardware will you run it on? Will you use a general purpose? I see a lot of IoT applications in college projects, right? Students come up to me and they bring in solutions which are run on a Raspberry Pi. A Raspberry Pi is as good as having a laptop. It runs a full OS. It runs a Python environment. How different is it from running the code on a laptop? Almost none. But I will never build an application with a Raspberry Pi because it's too expensive. It has, 5 HDMI connectors. It has network connectors, which I don't need probably in my application. So I have to be cost sensitive. I will use a processor that fits the requirements of my particular application. So specialization will deliver top performance in one niche, whereas generalization will deliver resilience in many applications. All right. Let's look at another part, lifetime versus data fidelity. Do I really need high fidelity data, right? For those of you who haven't seen it, that's the original Mac, right? And this is particularly important if your application, for whatever reasons, runs on battery power, or your end device or your edge runs on battery power. Do you prioritize the lifetime of the edge, right? As in, let it operate for as long as possible. This is especially true when there is no harvestable energy that can drive the system, right? So if you are looking at space applications or things like that, lifetime becomes very, very important. Or do you send out data as much as is possible? Is it a high fidelity system? And a high fidelity system will consume more power, it will consume more storage, and it will shorten system lifetime. So if you are running a high fidelity system in your topology, then there has to be an appropriate mechanism to power up that device. And it has to be on line power, or there has to be a source of energy for that particular device. Right. Last but not the least, let me also bring into this aspect of communicating versus storing. How much do you communicate? How much do you store? For how long do you store? Do you communicate your entire sensory data that you have acquired, right, to a centralized location? Do you transmit it and then wait for an acknowledgement and then delete it? Or do you transmit small patterns from your source signal and say that, hey, do you want me to send the rest of it? Do you keep a backup? More storage means that there is less immediate bandwidth use. So I can save, I can store for a while I am clearing out, trying to figure out whether I should be transmitting it or not. And if I get a decision that, hey, I don't need to transmit that, I can probably dump it. So it gives us better resilience. If I use more storage, it gives me better resilience to intermittent connectivity. But if I lose my device, then that entire aspect is gone. So there is the risk of data loss if the device fails before the upload. Right? Why did I talk about this? Right? I talked about all of this because when you are building out a solution, these are knobs that you have. These are various knobs that you have in order to tune between, compute or communicate, or carbon emissions and performance, or security and usability, or latency and consistency. These are all knobs, and any particular solution, right, is going to have a combination of this. Like it might trade off higher compute versus higher data fidelity for one application, right? You might look for a more generalized hardware implementation for another application. It depends on your application. And that's what systems designs are all about, right? What are the trade-offs that are driving your solution, right? I think I'm going to conclude here, but there were a few more slides. I'm just going to give you an overview of them, because if we look at these applications from an application perspective, right, we see that there are different scenarios where there are different knobs that can be used, right? If I look at cellular or Open RAN networks, if I look at defense or tactical systems, right, what are their trade-offs? If I look at entertainment systems, CDN systems, what are their trade-offs? Enterprise systems, right, what are their trade-offs? Each of the scenarios are going to be very, very different, right? I wanted to leave you with that thought process that these are all going to be very different scenarios. And as systems builders, we have to take that scenario into account, right? Yeah. So, questions?
Thank you. Thank you so much. Participants are requested to unmute themselves and ask questions, if any. Mr. Roychowdhury has given us so many tips, or so that our thought process may trigger. So, esteemed faculty members who are attending this course, if you have any question, please ask him. He has tried to cover different aspects. Any question from your side, participants?
So my philosophical take of the whole thing is a lot of computer systems that we build, a lot of computational systems that we build are based on our personal experiences. They are based on our interactions, right? And what our thought processes on societal existing societal systems are, right? So that reflection, I think, helps us build better systems, right? So that's what I'm going to leave you with. If there is a question or two, I'll take that. Otherwise, we'll bring the session to a conclusion.
Exactly. All the systems you have rightly pointed out in 1990s towards the Y2K problem was that time it was very much prevalent during 1998, 99. What will happen to the computer system in 2000 when 2000 comes? Because
Right.
before that, it was DDMMYY, not 4-digit Y. So year was only 2-digit, and that time it was very difficult situation for those who were working on computers and all. And now the system has totally changed. And after 2000, there was a drastic change. So definitely you have covered the whole era where we grew up learning different types of computers and all. Thank you so much.
My pleasure.
Let us take up any questions that comes from the participants. Is there any question? I don't think.
I think people got tired.
Maybe it's Saturday afternoon.
Saturday afternoon. That is true indeed.
But definitely they're going to get some insights when they will really visit this lecture once again. Yeah, all the videos will be shared to them, and definitely this is going to be a game changer in their life. That much I can.
Purposefully did not get into technicalities and code bases and things like that. One of the reasons being, let's use this session to use this as a reflection on what does the field stand for, right? And what are the core foundational challenges? Let me put it this way.
Yes.
Because systems design is not something that we teach in our curriculum. Software engineering is something that we barely scratch the surface of, and we not preparing a generation to build systems and understand the challenges of building computational systems, distributed systems per se. Right.
Yes, typically our syllabus is not covering all those aspects. Anyway, so Shoma madam, are you there? Shall we conclude this session? Shumit sir or Shoma madam, are you there?
Yes.
So thank you once again, Mr. Roychowdhury, for this wonderful session. Okay, one question came up just now. Many new information, sir, but to ask, we need a detailed knowledge. So next time we may ask. Okay.
So yeah, in general, yeah, I think that's what that's one of the things that we have seen in our university during our university days, right? Is we used to have something called seminar courses. And seminar courses was essentially when a faculty wanted to try out a new area, right? So what they would get is they would get 10, 12 PhD students into a course. We used to have the 600 level courses. Essentially, everybody would read 2 papers and present during our meeting time. So if we had 10 people, so 20, 40 papers were reviewed every week over the entire semester. So that gave us a good pool of maybe 500 or 600 papers to understand a particular area, right, before we did any research on that. while AI systems are good at summarizing lit reviews, right, it does not recreate the experience of reading those papers in our own mind, right? It does not help recreate those structures and thought processes for us to be building on top of, right? So definitely use that model. See if some of your curriculum, some of your courses that you are offering, you can convert them into seminar courses, asking students to come prepared to present a particular paper from a particular topic, right? And collectively gain knowledge about a particular area. That's, I found, a very, very useful way of bootstrapping our research area.
Okay. Thank you. Thank you for the nice suggestion. Definitely, if possible, we will try to incorporate those things.
Thank you.
Okay.
Thank you.
Thank you. Exactly.
Bye-bye.
Okay. Thank you.